The world around us is vast and full of treasures. There are so many things we can only catch glimpses of, and sadly it may take years to understand them. But thankfully, there is hope, as proven by a mystery that took almost 100 years to be completely unveiled. Keep watching to see how astronomers finally solved a 90-year-old space problem. Astronomers published the first image of the supermassive black hole at the Milky Way center. It's known as Sagittarius A star, SGR A star, and is situated where the constellations of Sagittarius and Scorpius meet. The supermassive black hole is subtended at an angle of only 52 microarc-seconds in the sky, but is 270 light-years away. Therefore, imaging this black hole is like pointing a telescope at a moon object the size of a donut. The technique used to create this black hole image was developed over several years. It represents an essential development in computational physics, which is at the core of the contemporary study. However, this fascinating tale started about a century ago, before radio astronomy began. What therefore transpired back then that prompted astronomers to concentrate their equipment in this area of the sky? What distinguishes this photograph from the supermassive black hole of M87 that was published in 2019? The most crucial question is, why is this image so crucial to physics and astronomy? Radio signals from deep space. Beginning in the 1930s, the first radio waves from space were found by Carl Jansky, who is generally regarded as the father of radio astronomy. In 1928, Jansky joined the Bell Telephone Laboratories research team and was given a difficult task. For use in transatlantic radio telephone service, Bell Labs sought to examine the atmospheric and ionospheric properties utilizing short waves between 10 and 20 meters. Carl was asked to investigate any sporadic static sources that might interfere with a radio voice transmission in his capacity as a radio engineer. To do this, Jansky conceptualized and created Jansky's merry-go-round antenna system. After a thorough study of the data gathered over numerous, painstaking months, Jansky distinguished between three types of static: a weak signal brought on by far-off thunderstorms, a stronger burst induced by nearby thunderstorms, and the third sort of burst that produces a constant hiss. One of the strangest things ever to be recorded was this third signal. It was the first known detection of an extraterrestrial radio signal, and according to Carl, the signal came from the Milky Way's galaxy's nucleus. Additionally, Sagittarius was the constellation where it was most prominent. By constructing a 30 meters dish antenna, he hoped to continue his investigation into the enigmatic cosmic signal. Carl was transferred to a different project by Bell Labs, who saw the assignment they had given him as finished. But the peculiar signal that Jansky had noticed wasn't ignored. Astronomers soon made the connection between the galactic center and this brilliant radio source. Two scientists, Bruce Ballack and Robert Brown, used the radio telescope at the U.S. National Radio Astronomy Observatory in 1974 to investigate the Milky Way center. In the area, they discovered a tiny core that was strongly generating radio waves. It was given the designation Sagittarius A star since it was the first radio source discovered in the constellation of Sagittarius. It was thought to be quite thrilling when a radio source at the galactic center was discovered. Asterisks are used to indicate an atom's excited state. Additional observations supported that instead of being a far-off background object, the star was a component of the galactic center. It was also discovered to have a mass that was compressed into a small amount of space by about 5 million times that of the Sun. These variables all indicated that the Milky Way's core is located in this area. But there was one thing that was always a mystery. Is Sagittarius A star a supermassive black hole or something else? Astronomers could not see Sagittarius A star in the optical spectrum due to the 25 magnitudes of extinction brought on by the presence of gas and dust between the source and Earth. Two teams led by Reinhard Gonzal and Andrea Ghez began analyzing the infrared radiation from the Sagittarius A star area to find an answer to this question. They found dozens of stars within 0.1 light-years of Sagittarius in the early 1990s. One of these stars was determined to have an orbital period of only 16 years, and at its closest approach to the main radio source, it was within 17 light-years or 120 times the Sun's distance. Researchers calculated that Sagittarius A star contains a mass of 4 million suns within an areal space that is similar to the size of our solar system, after examining the distances, speeds, and orbits of S2 and several other stars in this region for years. This configuration was feasible if Sagittarius A star was a supermassive black hole, as opposed to a mass of degenerate fermions or a cluster of dark stellar objects. Black holes are naturally invisible. They have an unbreakable gravitational pull that permanently traps any light that enters their gravitational abyss. However, the light continues just past a black hole's point of no return, and its patterns, similar to a photonegative, can disclose a black hole's hidden presence. Gonzalez and Guez established the existence of a black hole in Sagittarius after many years of non-stop observation and data processing, a star located in the Milky Way's core. 2008 saw the announcement of the outcome, and 2009 saw its publication in the Astrophysical Journal. The study, according to Gonzalez, the head of the research team, has produced what is now regarded as the strongest empirical proof that supermassive black holes are genuine. The galactic center and stellar orbits demonstrate beyond a shadow of a doubt that the central mass concentration is a black hole. Gonzalez and Guez were awarded one half of the 2020 Physics Nobel Prize. The first public picture. Based on radio interferometer data collected in 2017, the first image of Sagittarius A star was made public on May 12, 2022. Although technically speaking, it is an image of the accretion disk surrounding the horizon of Sagittarius A star. It further established that the object is a black hole. Data from 8 radio telescopes at 6 different places were gathered, and processing it took 5 years. There was almost 60 terabytes of data generated, which, if printed on paper, would have reached the moon. The picture resembles one that was made public 3 years ago when the Event Horizon Telescope captured a photograph of the supermassive black hole known as the M87 star that is at the center of Messier 87. But the two black holes differ greatly from one another. M87 vs. Sagittarius A star. To start, Sagittarius A star is situated in the midst of a spiral galaxy, whereas M87 star is at the center of a massive elliptical galaxy. Additionally, the M87 star is located approximately 54 million light-years away from our galaxy's supermassive black hole and is about 1,000 times more massive than the Sagittarius A star. The most intriguing feature is that the M87 star is active and has a plasma jet extending from it 50 light-years away. Although Sagittarius A star is not currently active, 2 activity surges have been seen in the past 10 years. NASA reported seeing a record-breaking X-ray outburst from the Sagittarius A star on January 5, 2015 that was 400 times brighter than usual. Astronomers speculate that the strange occurrence may have resulted from an asteroid fragmenting as it fell into the black hole, or from the tangling of magnetic field lines in gas entering the Sagittarius A star. The Sagittarius A star suddenly brightened on May 13, 2019, becoming 75 times brighter than usual, indicating that the supermassive black hole may have come into contact with another object. The similarity of the photos reveal that gravity predominates close to the event horizon, despite major variances between the black holes. Einstein's general theory of relativity can be tested near the heart of our galaxy. The future. As the EHT grows and more telescopes are added to its virtual array, the researchers anticipate gathering more data on Sagittarius A star and other black holes in the future years. As the telescope array is expanded and improved, Colin Lonsdale, director of MIT's Haystack Observatory, claims that the methods created for Sagittarius A star will pave the way for amazing EHT images and scientific discoveries. Only the brightest features are visible right now, so the team will work towards sharper images of the ring. Additionally, they hope to capture fuzzier substructures and anticipate seeing something more specific and distinctive from the first donut. It sounds like we have some interesting discoveries waiting in the future. Let us know in the comments below what you think they'll discover next and what you think about Sagittarius A star.